We've now talked about infection models at the population level, and we're interested in moving forward to considering the network effects, where again, the adjacency matrix A captures this heterogeneous connectivity that represents which nodes or people are more closely connected with other nodes or people. So an easy thought experiment is to understand that if you have a population that is actually in two disjoint components in that once you look at the network connectivity, that you would expect there to be very little, if zero, essentially infection spread between those two different components of the entire network. So we can kind of use that as an inspiration for why incorporating the adjacency matrix is useful. What we're going to see is that the dynamics that we consider is quite simple and quite similar to what we saw at the population level, and the real difference emerges from the definition of the state. So at the population level, X represented the fraction of the population that was infected at a given time, and S represented the fraction that was healthy or susceptible, and R represented the fraction that was recovered. In the networked version of the SIR model, each of these terms is going to describe the state of a specific node. And so we're looking at, for example, node I, the state X. Now that we're representing everything about the network, we need a state, we need an X for each node in the network. So for node I, we're going to have an X value. For node J, we're going to have an X value. And so that means that this X vector is a vector of length n, where n is the number of nodes. And each element represents now it's not going to be the fraction because we're representing a specific node. So it's actually going to be the probability that that node is infected. And then Si, the ith element of the S vector, is now going to be the probability that node I is susceptible. So just as before, the probability that the node I is infected, susceptible, and recovered, those three together need to sum to 1. So that means that Xi plus Si plus Ri should be equal to 1, and that's true for every single node in the network. An interesting and very useful consequence of considering that these represent the probabilities is that if we take the sum of Xi over the whole population, so essentially over all of the elements of X, then we can get the expected number of people that are infected. So just like if you flip a coin 5 times, or say 6 times, the number of heads that you would expect out of 6 flips is 3. And that's simply because it's half plus a 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 half. And that gives you 6. And so with that same logic, by summing up Xi over the population, over all the nodes of the network, we can actually get the number of nodes that we expect to be infected. All right, so we said that the dynamics are going to be quite similar, and they are. Essentially, the infection, the change in the infected probability of node I is going to be related to, so this is whether or not I is susceptible, and this is whether or not one of its neighbors is infected. So the probability that node I is susceptible multiplied by the probability that node J, a neighbor, is infected, multiplied by the beta term, gives you, this beta again is that rate, and so that gives you that same term that we saw before in the SI and the SIR population level models. What's different is that we're going to use the adjacency matrix to connect, to essentially say whether or not I and J are neighbors. And so that's again this gating variable that says 0 if they're not connected, or non-zero if they are connected. And again, this could have weights in it, so you could emphasize the fact that, say, family is a closer connection than work colleagues. And so if a family member was infected, that would be more likely to pass on the disease than a coworker. So now we're dealing with probabilities, and so now we're going to take the rate times the interval of time, just like we saw in some of the derivations in the last video, multiplying that rate times this time to say the likelihood that you get infected, that you transmit that disease in the time step dt. So again, very similar structure. The really only difference is that we have to only pick the neighbors of the network, and that's given by this adjacency matrix. And now we're dealing in probabilities, so now it's not just the rate, but it's the rate times the amount of time, that delta t, or dt. And so now again, similarly, the probability that the rate at which we assign the probability for infection is now going to decrease according to the recovery. And again, the only change here is the fact that we're looking at the recovery of node I itself, and that instead of dealing with the rate gamma, the recovery rate gamma, now we're going to multiply it by that dt in order to say that's the probability of recovering in the instant dt. Similarly, so that simplifies these dynamics down to this. So that's just consolidating all of that. So that's our equation for the infection quantity x at node I. So following similar logic, and again, just from the notion that the terms have to be equal and opposite, these two terms have to be equal and opposite. So we have to make sure that we're adding and subtracting, because again, xi plus si plus ri has to be equal to 1 at all times for all nodes. So again, these terms are equal and opposite, and so we can build out the rest of the differential equations that model the infection spread. An interesting thing to consider here is that the value of the state at a given node is actually 3 values. So unlike what we've talked about kind of in the general dynamics on networks, we just said that there was a state and it was just xi. And now what we're saying is that this state actually has 3 components to it. So because they always have to add to 1, then there's really only 2 variables there. But still, every node has at least 2 variables, if not 3 variables, to represent its current state. Whereas in most of our dynamics, like diffusion, there's just a single number. So that is one thing that distinguishes it. So we'd like to be able to see a little bit more now that we've described the networked version of this. For the most part, the networked problem really needs to be simulated over and over again in order to really see what's going on, because it's very difficult to capture things about the heterogeneous connectivity in the adjacency matrix in an analytic way. But there are a few things that we can do. And so one of the things we can take a look at is, again, this epidemic threshold. And so if we take a look specifically at the time where the susceptible population, most of the nodes are susceptible, that means that this SI is in general close to 1. And so what we'll do is we'll take a version of this infection dynamics and we'll present it without this S term. So we'll assume that that SI is close to 1. And what that does is it allows us to get rid of this term that's related to I here. And now this beta can come into the sum. And we can also include gamma into the sum as well. And this is a trick that we saw similar to what we did in diffusion, where we pulled this in and added this delta function. So now what we've done is we've essentially defined this new matrix capital M. That's right here. And now we can write our differential equation as dx dt as a function just of x. So we've gotten rid of the dependence on s, and mainly that's just based on the assumption that we're early on in the infection spread and that most of the nodes are susceptible. So with this M matrix, we can then study some of the characteristics of this differential equation, where again, this is a differential equation of just one single variable, and that allows us to do some more sophisticated analysis. So in studying the dynamic behavior of this differential equation of just x, we can use an analysis that's very similar to what we did in diffusion, which is the idea that we're going to represent the state x as a linear combination of its eigenvectors. And the coefficients, these AI terms, because this is a function of t, that really AI is also going to become a function of t. So this is very similar to what we did in diffusion. And so what enables this is the fact that the eigenvectors of A and the eigenvectors of M are just the same. And that's really just because this identity matrix doesn't change the eigenvectors. Because if I multiply, this is the eigenvector-eigenvalue equation, if I multiply M by this vector V, each term, because it's an eigenvector of A, we also get a term that's related to V, and because the I doesn't change V, we also get V back again. And so that very easily makes new eigenvalues, so the eigenvalues are shifted by this gamma over beta, but the eigenvectors are the same. So we can still expand the states according to the eigenvectors of A. And so just like we did in diffusion, we can plug this x into this differential equation to form n of these equations that are about just the coefficients. And so we can look at the different AI coefficients and study their behavior. And again, that's a single variable differential equation, which allows us to separate it and solve it as this exponential solution. And importantly, the coefficient that arises here is this beta times the eigenvalue minus gamma. And so what you're going to see here is that if essentially all of these ought to be negative, if we want the x state to be decreasing. In some cases, these could be positive, and effectively the most positive one, the lambda that creates the most positive exponent here is going to be the one that dominates the solution. It's going to be the one that has the biggest magnitude over time. And so then it's if we call lambda 1 the largest of the positive eigenvalues, then this is the criterion for the epidemic threshold. So if if this exponent is equal to 0, it just stays flat. The x value stays flat. But if this becomes positive, then you're going to grow the amount of infection in the network. So one of the ways to think about this is that the new thing is that if we got rid of this, then this would be very similar to the expression that we had at the population level, where beta over gamma, if that was greater than 1, you had an epidemic, and if it was less than 1, you didn't. Here, the introduction of this eigenvalue is interesting because it's a way of quantifying how the network properties impact the disease spread. And so, for example, if this lambda 1 is small, then what this does is it makes it more difficult for the disease to spread. Whereas if this lambda is large, if this eigenvalue is large, then it makes it easier for the disease to spread for the same values of beta and gamma. And so that means that different network architectures will have different characteristics. So you could imagine, for example, comparing a star network with a path network. These will have very different eigenvalues, and if you just think about the disease spread in this context, it's going to be a lot easier for it to spread in one of those than, for example, the other. So this eigenvalue is a way of quantifying that in the context of the epidemic threshold for the networked model. So I mentioned that it's difficult to characterize all of the analytically the response of a network to an infection spread, an SIR infection spread. And that's because the A matrix can be highly sparse and highly complex, which gives complex behaviors. But one thing that we are able to analyze is the late time properties. And so by late time, we mean that we let t go off to infinity and we let the whole disease play out, and then we understand what are the properties about the spread of that disease. Again, that doesn't give us information about the transient behavior, about how it evolves over time, but it kind of tells us where we end, which at least will tell us something about the epidemic nature of an infection. So if we look at the SI model, this is a little simplistic, but we're going to start with some patient 0. So that means some initial infected person, or it could be possibly a set of people that is infected. And then those people are going to infect their neighbors with some probability. And so that probability is related to the infection rate multiplied by the amount of time that we're thinking about each step taking. And so it's pretty easy to see that if beta is greater than 0, and if you let time keep going, then these nodes have multiple tries to infect their neighbor. And so eventually, we expect that all nodes will go ahead and infect their neighbors in the end because nobody recovers. And so ultimately what that means is the fact that if you have an initial infected node, every node that you can reach from that initial set of infected nodes will also become infected. And so in a lot of ways you can think about this as just using our breadth first search and expanding out from our infected nodes. And so the only saving grace would be as if you disconnected the network, because again, nobody recovers in this model, and so the infection is really just contained within the components of the network. When we move on to looking at the late time properties of the SIR model, things become a little bit more interesting because people can recover from the disease before, so they can't perpetually be infectious and continue to infect their neighbors forever. So again, we start with some initial infected set of people, and again, those people infect their neighbors with a given probability, and we'll say that probability is P. And again, in this case, because people recover, we're going to say that the nodes stay infected, or importantly infectious, for a specific amount of time, and that amount of time is tau. And so we'll just say that that's going to be the same for everyone. So that expected recovery rate, that's going to be the same for everyone. And if we know that amount of time, then we can back calculate the probability that a node that becomes infected would infect their neighbors. So over the whole window, so notice this is no longer a function of d tau, it's actually a function of tau. So we know that the person's going to be infectious for an amount of time tau, and so the probability then that they would pass on the disease would be this exponential quantity, 1 minus e to the minus beta tau, that we calculated before. And so we can do this simulation kind of in real time, where we keep updating the states x, s, and r as we go about. Another interesting way of doing this, however, which is more computationally kind of advantageous, is the fact that we know that this is the probability that a node is going to infect its neighbor. So if we have an infected node and it's got a neighbor, then essentially this edge represents whether or not this node is going to pass on the infection to the other node. And so it does so if they're connected and if this probability, with this probability. And so one of the ways we can simulate this, essentially if we're not interested in the whole time and we're just interested in effectively computing from an initial condition, what is the final steady state values of x, s, and r, then what we can do is then we can flip coins that represent these edges. So if this edge comes up as a tail, so it's going to communicate the disease with this probability. If we flip a coin and with that probability, and so it's no longer a fair coin, 50-50, but now it's flipping heads with probability P. If that coin comes up heads for that edge, that means that this node, this first node, will indeed infect its neighbor. If it comes up as tails, then the disease is not communicated. So this is a random process because we're flipping these coins and we're getting a realization. And so it would only make sense is if we continue to do this over and over again. So we try a coin flip for all edges and then see where the network communicates the disease. And then we do it again, and we do it again, and we do it again, and we get an average over this. And so essentially, when you get the tails, this is effectively saying that this edge doesn't participate in the communication of the disease. And so one way to think about it is that we're actually removing it. And so this gets back to the notion of percolation. So when we flip the coin and we get tails, we remove it from the network, and then any of the remaining edges propagate the disease in the late time. So that means that if that person ever did become infected, they would pass on the disease along that edge. And so then it's just a question of tracing the edges from the initial set S that is infected. So very similar to the SI model that we just saw, their late time properties, but what we do is we first do a probabilistic percolation of the network based on this probability, where again, remember this probability is dependent on the infection rate and also on the recovery rate. So tau is related to the recovery rate. And so what this is telling us is, again, this epidemic threshold that we identified in the population model doesn't always have to be the case if, for example, the infected nodes are somehow contained within a less well-connected piece of the network. And so it's also true that even if it is in a relatively well-connected part of the graph, that a random selection of these coin flips might cut it off from propagating throughout the rest of the graph. And so this kind of plays out. All of these different trials represent different situations and how the disease might spread. But again, to get a full picture of expected behavior, we would have to repeat this process over and over again and kind of average out what would happen across many of these different trials.